In this first lecture, I would like to talk about research of computation itself. As a first topic, let me explain a brief history of the early stage of this research. We learned that the fundamental components of computation is +-1 operations on data and simple repetition. Well, you may wonder whether all things can be expressed just with this. In recent years, we have AIs and quantum computing. People may wonder just the same, whether that could express all that we wish to express. In fact, based on early research on computation, we reached the conclusion that +-1 and the simple repetition are enough to express computations. Such investigations can be considered as the starting point of the research of computation. Let's look at the history of this study. Of course, computation has been conducted from ancient times, and there has been a variety of studies concerning computations and calculations. For example, Euclid of ancient Greece proposed an algorithm for computing the greatest common divisor, which is known as the Euclidean algorithm. Or there have been computational studies concerning procedures such as how to solve quadratic equations through calculation. Also, many attempts have been made from long ago to make computational devices. In that process, the question, what is the nature of computation, has been considered. For example, one of the famous mathematicians, Leibniz, a contemporary of Newton, is said to have created a preliminary computational device. But let me focus on the investigation leading to this claim. We can specifically identify the starting point of this investigation. In the year 1900, just at the dawn of the 20th century, Hilbert, a leading mathematician of that time, suggested at the International Congress of Mathematicians that there were 23 problems which would likely become important during the 20th century. Among them, the following question was asked as the 10th problem. Can we find a method to determine whether a polynomial Diophantine equation with integer coefficient has an integer solution? In other words, how to compute this integer solution? Despite of efforts of top mathematicians, it seems difficult to consider such a method. Then people started wondering it may not be possible. But if so, the task of mathematicians is to prove its impossibility. But then we need to define what we mean by method. So people started to think about what method is, or in our word, what computation is. This is one of the beginnings. In the early 1930s, between about 1932 and 36, multiple mathematicians independently came up with their own forms of computations and suggested them as the fundamental components of computation. They were Alonzo Church, Alan Turing, Emil Post, and Stefan Kleene, to name but a few of such mathematicians. There were several more. It is said that Hilbert's questions were the starting point of research into this field, but there were others, such as Kurt Gödel, who had been studying the fundamental question concerning mathematical proof. This was around 1932, but his research was also considered as a major trigger as well. Anyway, these computational methods had been independently proposed. But quite interestingly, they were proven to be equal. That is, each model is of equal value, exactly the same capability. Note that these methods were quite different. That is, everybody was thinking about the fundamental components of computation from different angles. Then, since they were proven to be all equivalent to one another, they all started to realize that they were all on the same thing and that there is no other way to define computation. Based on this investigation, these mathematicians have decided to consider anything that is composed of these fundamental elements as computation. This is now called the Church-Turing thesis. It is said to have been named by Creaney. This is not a mathematical proof or theorem. This is because it is not something that is provable, but a suggestion to define the notion of computation by any of these models. So, of course, if there is a new way to compute, then this thesis should be overwritten. By the way, our claim, that is the idea of using +1, -1, and the simple repetition for fundamental components of computation, is similar to the notion of recursive function. Now, let me continue the history. So, starting from the 10th problem of Hilbert, mathematicians proposed various models of computation and realized that they are all equal, essentially equivalent. So they concluded that it should be okay to define the notion of method or computation by any one of such models. What is more important of this investigation is the discovery of the following fact, stated as a theorem. By using his model, Turing proved that there are functions that are not computable. In fact, he gave some concrete example of incomputable function, that is the halting function. So what he proved is that there is a limit of computation. This shocking discovery have people recognize the meaning and importance of those proposed computational models clearly. Now, what about the Hilbert's 10th problem? This took a long time from the first theorem showing the limit of computation. But finally, in 1970, Yuri Matyasevich, a graduate student at that time, proved that the computational task that is asked by the 10th problem of Hilbert was indeed incomputable. That is, the 10th problem was solved negatively. Then, it would be natural to wonder whether something that people from long ago came up with still hold up in this modern age with the development of artificial intelligence and quantum computing. Well, the notion of computation has been studied in depth after Turing et al., for example, to obtain this negative solution to the problem of Hilbert. Through such studies, researchers gave many strong evidence supporting the Church-Turing thesis. Furthermore, whenever new computation model, such as quantum computing and so on, appears, it has been checked that the new model does not change the notion of computation. Therefore, we can still claim that even now that the essence is the same.